You let me know when we're going.
Yep.
Welcome, everyone. Hi, it's nice to see so many of you joining us. Welcome to the July NASA Night Sky Network member webinar. We're hosting tonight's webinar from the Astronomical Society of the Pacific in San Francisco, California, and from our home offices in New York City and Berkeley. And we're excited to welcome our guest speaker, Dr. Cynthia Phillips from NASA JPL. I want to welcome everyone joining us on the live stream tonight. We're happy to have you with us. These webinars are monthly events for members of the Night Sky Network. Got it. We stream them live, and we've got a wealth of past topics available on our YouTube channel. You're welcome to take a look at those. The Night Sky Network is about 400 astronomy clubs across the US, and these clubs host regular observing and other astronomy goodness all year long. So I encourage you to check them out. I'll throw some links to that in the chat in just a minute. For more information about the Night Sky Network and the Astronomical Society of the Pacific, I will put those chats in there, put those links in the chat in just a minute. In fact, this talk is full of great resources. I'm going to be putting a lot of things in the chat, and hopefully you'll be able to chat back with us. We'll put those in the YouTube description as well after we finish tonight, so you'll have access to all those in perpetuity. So we have a couple of announcements. I want to welcome Kat Trosch with a few announcements. Go for it, Kat.
Hi, everyone. So first, I did want to announce the winners of our quarterly prizes. They were selected just today, and you all should be getting your Eclipse Party Packs very soon. This is the Astronomical Society of Kansas City, Warren Rupp Observatory, the Astronomy Club of Asheville, Community Observatory, and Fort Worth Astronomical Society. So congratulations, you'll be getting a big box of viewers and other wonderful eclipse tools to help you do outreach with your communities and to get you prepared for the annular and the total solar eclipses in October and in April, respectively. So speaking of eclipses, tonight's webinar prize, after you have listened to our wonderful webinar, listened to our wonderful speaker, and have completed the survey, would be 5 passes to the Astronomical Society of the Pacific 2023 virtual conference, exploring the arts, culture, and science of solar eclipses. And that is August 18th, 2023. And again, it's all virtual, so you don't have to do anything except kick back and listen to a bunch of great talks and learn a little bit about the art behind eclipses, because remember, it's not just STEM, it's STEAM. So there's art in there. There's art involved in science as well. And one more, just to throw another incentive at you. NASA has announced that they have partnered with some folks, and they are going to ask astronomers if they are willing to live stream the annular eclipse on October 14th, 2023, with the possibility of coming out of Caryville, Texas, and Albuquerque, New Mexico. And if we have any astronomers in or around the vicinity of those locations, you are more than welcome to complete the NASA form that Vivian has dropped in the chat, and just give them your information. And if you're selected, you will be able to participate in a NASA live stream for the annular solar eclipse this October.
Thank you so much, Kat. I think they're even looking for people outside of that area as long as you are on the path of annularity. So feel free to fill that out if you're interested. All right. For those of you on Zoom, you can find the Q&A window at the bottom edge of the Zoom window on your desktop. Feel free to let us know if you're having any technical difficulties besides the chat not working. You can also send us an email at nightskyinfo@astrosociety.org. And if you have a question for our guest speaker, go ahead and put those in the Q&A window. It'll help us keep track and know if we have answered your questions or not. All right, we'll get to as many of those as possible at the end of the talk tonight. So thank you so much for joining us. This month, we are welcoming Dr. Cynthia Phillips. She's a planetary geologist at NASA JPL. Her background's in surface processes on icy satellites, and she's an expert in image processing. I know many of you out there are as well. She gets to do it for NASA. She's a project staff scientist on the Europa Clipper mission, as well as the project science communication lead. She has degrees from Harvard and a PhD in planetary science from the University of Arizona. She also, I just found out, worked on the Galileo mission back in grad school. And so she has been waiting decades to see the next images of Europa up close. I want to welcome Dr. Phillips. Thank you so much for joining us.
Excellent. Thank you so much for the invitation to speak. And I'm really looking forward to sharing why I think Europa is so amazing with everyone who's attending tonight, as well as talking about the Europa Clipper mission, which is going to go back to Europa and see it like we've never seen it before. So let me share this. All right, that look okay?
Looks great.
Okay, fantastic. So as Vivian said, hi, I'm Cynthia Phillips. I work at NASA JPL, and I'll be telling you all about Europa and Europa Clipper. So Europa, it's a moon of Jupiter. Here it is. It's behind me, kind of looking over my shoulder, and it's here in the background. And Europa is a really fantastic world out in the Jupiter system. It's about the same size as Earth's moon, but it looks very different. And so it's one of the 4 Galilean satellites of Jupiter that were discovered by Galileo. This is his original sketch up here. And we now know from images taken mostly by the Galileo spacecraft in the late 1990s, that these 4 moons, these 4 large moons of Jupiter, are really amazing worlds in their own right. When we look at them, they're in order here from their distance from Jupiter. So Io is the closest moon to Jupiter, and sometimes we call it the pizza planet because it is actually the most volcanically active body in the solar system. The surface is covered with lava flows, there's active eruptions, there's bright kind of sulfur deposits, as well as sulfur dioxide frost, and it's this weird and wonderful place. But when we're thinking about maybe places for life in the solar system, not a good place to go look. Europa is the next moon out, and it's further from Jupiter. It is covered with a layer of ice at the surface. And under that icy layer, we have evidence that tells us that there's actually more liquid water than all of Earth's oceans combined. And when we look at the surface of Europa, we see that while, again, it's about the same size as Earth's moon, but it looks very, very different. Our own moon is an old, cratered, battered, rocky body that's been battered for 4 billion years of solar system history with impactors. These bodies out in the outer solar system have also been hit by impactors. But if you look at these images, you can see on Io we have yet to find a single crater. On Europa, there's a few craters. On Ganymede, we have some, and then on Callisto, there's a lot of craters. And scientists use craters as a proxy for surface age. Basically, if we know that everything in the solar system gets hit by impactor, by comets, asteroids, meteorites, chunks of solar system debris. And so if you have a world where there's no geologic activity, the surface just accumulates those craters, and you have an old world like the moon. If you look at a world like Callisto, you can see that the surface is really covered with craters. So that tells us it's a pretty old surface. Ganymede, there are places that are higher and lower crater density. And so there we can get into actually dating different terrains on the surface. Some look older, some look younger. We see evidence of maybe some old kind of tectonic activity. Places like Europa have very few craters. And then places like Io have 0, none that we found so far. So that tells us that Callisto's surface is very old, Io's surface is very young, Europa's somewhere in between. The evidence that we got from the Galileo spacecraft tells us that Europa has an average surface age of about 50 million years, which is very young by solar system standards, whereas Ganymede and Callisto are a bunch more in the billions of years old. So here's why we think Europa is so amazing. How does it support that subsurface ocean of liquid water? And why do we think that water is there in the first place? We do think that there are oceans of liquid water beneath the surfaces of Ganymede and Callisto too, but they're much further down. They're much further away from the surface. And also they're sandwiched between 2 layers of ice. And so for reasons that I'll get into in a minute, that makes them a lot less interesting, at least astrobiologically, than a world like Europa. So here's what Europa looks like up close. The Galileo spacecraft took some amazing high-resolution images that showed us that this world is just covered with cracks, with ridges, with bands, just this detailed texture, this interwoven surface appearance. And so these are some of the ridged plains that we call it on the surface. There are regions that look kind of like icebergs. This is what we call chaos terrain. And these are locations that look kind of dark and fuzzy. This is a famous one called Connemara chaos. It's kind of located right under this X-shaped feature that I'm pointing to here on the left. And what we see when we zoom in is places where the surface, pieces of the surface, blocks, have actually broken apart. They've translated, they've rotated, they've even tilted in some places. And then they've sort of refrozen into their new positions on the surface. So that tells us that some kind of disruptive mechanism took place that changed the surface from beneath. And we also see a few craters. This one here is the Pwyll impact crater, or Pwyck if you speak Irish. And basically what we see here is a very young crater. This is about 26 kilometers in diameter, and we have these bright rays that stretch off in all directions. This is similar to what we see in bright rayed craters on places like the moon as well. And there are also weird spots that are called lenticulae, which is Latin for spots or freckles. And these are places where they're very small, kind of dark regions. Some of them don't have any color and they're just kind of little pits or domes. Some of them have kind of this reddish color to them. The reddish materials that we see on the surface seem to be associated with places where some sort of material was brought from the subsurface up to the surface. And that gives it this reddish appearance. And all the images that I'll show in this talk, they're what I call enhanced color products. So Europa's surface is really, it's a very bright surface. It's one of the highest albedo objects in the solar system, actually. And so the contrast on the surface is quite low. And when we look at these images, if we didn't stretch them and kind of really enhance and amplify the color, bring in filters that go from, say, violet out into the near infrared and compress and show those as red, green, and blue, those are used to basically enhance the very subtle contrast differences on the surface. And what these reddish features tell us is these are locations where we think there's been material from the subsurface brought up close to the surface or even onto the surface. And so again, those are really interesting locations. So here's what we think Europa's interior structure looks like. We have an icy crust on the surface that's about 10 to 50 kilometers thick. And then underneath that is this liquid water ocean layer. Below the ocean is a rock layer, and then we have a metallic core. So, Europa's surface, it's not just an ice ball. It has a pretty substantive rocky and then metal portion as well. Actually, the outer moons, Ganymede and Callisto, have a higher fraction of ice proportionally, but it's Europa that has the largest liquid water layer. And so Europa actually has more water than all of Earth's oceans combined. So, we think of Earth as this water world, but on Earth, the water is actually really this very thin kind of skin that's on top of a ball of rock. And Europa is similar, but it has more water than Earth. So when we think about life, when we think about the prospect for life beyond the Earth, all life on Earth is dependent on water. And so we know there's life on Earth. We know that there's this giant ocean on Europa. It could have present conditions for life. And so this is where I tweak the Martians a little bit. Mars is great, right? Our Mars exploration has followed this mantra of follow the water. They've looked for signs of ancient, riverbeds and fluvial activity on the surface of Mars. And yes, it looks like Mars probably did have a period in its past when it was warmer and wetter, when the atmosphere is thicker, and when maybe life could have formed and flourished on the surface of Mars, but that's in the past. So when we're studying Mars, we're really looking for old, dead, fossilized life. But on Europa, there could be life there today. There could be present conditions for life. And so if we're thinking about follow the water, in my opinion, at least, we should follow it all the way to Europa, just, past Mars. So why is there this ocean? Why is a world that's 5 times further from the sun than we are on Earth, how could it possibly have liquid? And it's due to tidal heating. So basically what happens is these animations are showing, and here, let me play this one again. Europa's orbit, as it orbits around Jupiter, it has a non-zero eccentricity. So eccentricity is the degree of non-circularity of an orbit. If you have just a single satellite in orbit around a planet, you would expect over time for that orbit to become circular. The distance between the satellite and the planet would not change over the course of its orbit. And so the gravitational force on the surface would remain the same as well. But in the Jupiter system, we have Io, Europa, and Ganymede, 3 big moons that are in a resonance. Basically, every time Ganymede goes around once, Europa goes around twice, and Io goes around 4 times. This means that these moons line up at the same place in their orbit each time, and they tug on each other. So these tweaks, these tugs, basically create what's called a forced eccentricity. They produce these non-circular orbits that are very stable over billions of years. And so it's this forced eccentricity on Europa, which means that the distance from Europa and Jupiter changes over the course of an orbit. And so that means, as you see here, this kind of potato-shaped Europa is very exaggerated. When it's closer to Jupiter, it gets stretched out. When it's further away, the surface goes back down. And it's this stretching and tugging, this pulling, this tidal squeezing that actually creates frictional heating. And so here again is what a cross-section might look like. So we're stretching and pulling, and this heat is placed in Europa's interior. And calculations show that that's enough heat to keep an ocean of water liquid over the whole 4 billion year age of the solar system. So here's what we think is going on. We have a cold, stiff ice layer at the surface. And then below that, we think we have a warmer kind of convecting, a flowing ice layer. And then beneath that, we have the ocean. And there could be places on the surface. Remember, I mentioned that chaos terrain, those places where these blocks were kind of moving around. It's possible that there could be plumes of material being ejected from the subsurface, but there's a buoyancy problem. The density, as it turns out, of liquid water is less than the density of solid ice. That's one of the reasons why frozen ice floats on the top of liquid. And water is one of the only substances that does this. It's very weird. But what that means is that it's very difficult to get liquid water up all the way to the surface. Maybe you could do it in a plume if you pressurize it or if you have some kind of non-ice components in there, but it's hard. But what you can do is you can get about 90% of the way there. And so one possibility is if you have a thermal plume, you have some kind of heat source that impinges on the bottom of this ice layer, maybe it could kind of make its way up to close to the surface. You could get kind of a subsurface melt lens of liquid that's close to, but not actually on the surface. And we think maybe that could disrupt the surface and create these features, kind of like chaotic terrain. Here's a zoomed in view of one of those iceberg chaos regions on the surface, where you can see there's these blocks and then there's this kind of matrixy material that they're embedded in. And so here's what it might look like if we assume that there's this model of what we call a melt lens, where there's liquid that gets close to the surface and maybe allows these blocks to move around. So basically, we think that Europa is one of the best places to look for life beyond the Earth. And that's because it has all the ingredients we think for life as we know it. It has water, so it has more than all of Earth's oceans. It has the right chemical elements. These are things like carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. They're materials that are fundamental building blocks of life. And we think that those materials are there from Europa's formation, and some could also have been delivered from impacts brought from comets and meteorites as they crashed into the surface. We believe that there's a source of chemical energy. So there's potential energy from hydrothermal systems if they exist below at the water rock interface at the bottom of the ocean. There could be places where there's warm material which heats and circulates the water through the subsurface, where it could pick up interesting oxidants and organics, interesting minerals that could then drive an ecosystem. As well as we also have radiation, which processes the surface. This is from Jupiter's strong magnetic field. That creates interesting compounds at the surface, interesting oxidants as well. And if those can be incorporated, if they can be worked down from the surface into the ocean, those could also serve as potential fuel, a potential energy source for a biosphere. And another really important point is that Europa has stability. Our models show that this resonance, which is what provides the heat source to sustain this ocean, has likely been there over the age of the solar system. So we think that this water world, this environment with potentially habitable ocean, has been there for 4 billion years. And so that element of time is really a very important component here as well. So what maybe could we find at the bottom of Europa's ocean if we went there someday? So this is not a video from a Europa submarine. I wish it was. That's maybe coming in the future, but not yet. But this is what hydrothermal vents look like at the bottom of Earth's ocean. So we used to think that the bottom of Earth's ocean was really just a wasteland, that nothing could possibly survive there. And then we went and looked, and this is what we found. We found these abundant ecosystems with all sorts of different kinds of, crabs and shrimp and fish and, just really amazing biodiversity at the bottom of Earth's ocean. And this ecosystem is almost completely independent from the sun. It does get some material that is created at the surface of the ocean, the photosynthesis layer at the top of the ocean, that then kind of falls down through the ocean. So it does kind of get a rain of some surface products. But really the bulk of the ecosystem is supported through these black smokers, these places at the bottom of the ocean where liquid is circulated through the crust and it picks up these interesting chemicals. So something like that could exist at the bottom of Europa's ocean. So for all of the reasons that I just gave you, NASA is going to send a new mission there. And the mission is called Europa Clipper. And the top level science goal is to explore Europa and investigate its habitability. And so habitability is a bit of a carefully chosen word here. We are, with Europa Clipper, we are investigating whether Europa could be habitable. Are there environments on Europa below its surface that could support life as we know it? So this is not a direct biosignature detection mission. It's not a mission to detect whether or not Europa is inhabited, but it's to see whether Europa is habitable. So could it support life, rather than going there with a magnifying glass and a microscope to actually look for cells. So that's an important distinction. But as a habitability mission, it would be a huge step forward in the understanding of life beyond the Earth, of the possibilities for life in the solar system. So the top level science objectives for Europa Clipper are to study Europa's ice shell and ocean, to study the composition as well as the geology of the surface. And it will also search for any recent or ongoing geologic activity, and it will perform some reconnaissance as kind of a secondary objective for maybe a future potential landed mission. And so here's what the payload looks like. There's a series of about 10 science investigations. The remote sensing payload spans the range from an ultraviolet spectrometer, there's a narrow and wide angle camera, there's an infrared spectrometer to look for surface composition, there's a thermal imager to look for hotspots, and then there's an ice penetrating radar, which we hope will be able to see through the ice layer. It may be able to sense those melt lenses within the ice shell. And depending on the configuration of the ice shell, how warm it is and how fractured it is, it may be able to see all the way through the ice layer and sense the top of the ocean. And then in addition, there's what we're calling an in situ payload. And so these are instruments that will be able to measure the composition of material that's thrown off the surface of Europa through charged particle and micrometeorite impacts. So as the spacecraft flies close to Europa, there will be a mass spectrometer which measures the composition of gases, as well as a dust analyzer that looks at the composition of dust particles that are thrown off the surface. And then in addition, there's a magnetometer and a plasma instrument to help to study Europa's space environment and the induced magnetic field, which is caused by the conducting salty ocean that moves through Jupiter's strong magnetic field, as well as a gravity and radio science investigation to help us understand the subsurface structure of Europa. Here's what the spacecraft looks like. It's big. It's a solar-powered spacecraft. So that means that we have these huge solar arrays. These are some of the biggest solar panels that have been flown to the outer solar system. And this is basically about 100 feet wide, tip to tip. So that's about 30 meters. We're talking the size of a basketball court. So this thing is gigantic. There's a Huygens antenna that's 10 feet long. It has 24 small 25 Newton engines, which are used for propulsion. It has a deck of instruments. There's the in situ instruments are on this forward pointed deck, and then the downward pointed instruments, those are the remote sensor ones, the cameras. There's a series of two large high frequency radar antennas, and then 4 very high frequency antennas. And it's an amazing spacecraft. So one of the big constraints when studying Europa is Jupiter's magnetic field. So basically what happens is Europa orbits within Jupiter's magnetosphere. And so this is Europa here as it goes around. And so basically what happens is that when you're close to Europa, you're in a really high radiation environment. And that's really bad for your spacecraft. And so one of the reasons why Europa Clipper is going to be a multiple flyby mission as opposed to an orbiter is just that, it's the radiation. So what that means is that rather than spending a long time in the radiation environment right by Europa, you can only survive in orbit for maybe a month. But instead, we're going to have a series of long looping orbits that will fly close to Europa, take observations, and then you get out of there. Then you move further away. And so basically, you have these gravity assists. And so these are what the ground tracks look like on the surface. So each flyby covers a different portion of the surface. And we're able to do about 50 flybys over about a 3.5-year prime mission to minimize our time in the high radiation environment right by Europa. And here's just kind of a cumulative dose map, a dosometer for the mission. And so what we're seeing is every time Europa Clipper, which is this, flies past Jupiter, you'll see there's this radiation meter, this sort of a virtual Geiger counter. So you see a spike in the instantaneous dose, as well as the increase in this bar. This is the cumulative dose. So you can see each time it flies close to Europa, it gets a spike of radiation, and then that total radiation is added to this cumulative dose. And basically, by the end of the mission, you'll see that the radiation is getting higher and higher. We're building up more and more cumulative dose on the mission. But the parts and the spacecraft, basically everything in the tour is designed to get us to that prime mission, those 50 or so flybys, comfortably within kind of a radiation design margin. And so this is what a potential tour might look like. We're in the process of finalizing what our actual trajectory is going to be, but it'll look something like this. So here's where we are today. We are working on building the Europa Clipper spacecraft, which is just amazing after having worked on this mission for, almost 8 years now, and having waited for 25 plus years since the Galileo mission to get to go back to Europa. So here's just some images of the propulsion tank. We have a vault shown here on the right, which is a shielded basically box where a lot of the sensitive electronics go. Here's some images of some of our instruments under development. This is what the magnetometer boom looks like. It's a compressed boom that basically expands out. Here's some of our cameras. This is one of the reason antennas being tested at JPL. And here's what some of these look like installed on the spacecraft. So this was taken just about a month or 2 ago. Here's one of our technicians in the clean room at JPL. And you can see here's our dust instrument, and here's our gas instrument, MASPEX and SUDA. And then over here on the left, this is the deck where a lot of the remote sensing instruments are. And so you can see here this kind of tube that's part of the camera, the narrow angle camera, so the ICE NAC instrument. This is the telescope for it right here on the left. And some of the other instruments are on this, the top of what we call the nadir deck as well. So this is what it looks like. And the spacecraft is being wrapped up in thermal blanketing. So once it launches, it's not going to look quite this cool. It'll just kind of look, gray and or silver and crinkly, I guess I would say. Here's what our solar arrays look like under development at Airbus in the Netherlands. And you can see with this human for scale, just how massive these things are. And you can watch the spacecraft assembly. This is a screenshot from maybe a month or two ago, since this picture was taken. So here on the right, we're seeing the propulsion module. Here on the left, we're seeing the vault. The door to the vault here is open. The nadir deck with those instruments is on top of it. So you can see there's that telescope. The ice NAC is up here on top. And since this picture was taken, the vault has been stacked on top of the propulsion module. So this thing is even taller now than it was back when the screenshot was taken. But there's a live feed, so you can watch. And if you go to this link here, bit.ly/ClipperCam, they're working 2 shifts now. So you can see them during the day, and you can also see them many evenings too, working to assemble this. And we also have a live moderated chat every Tuesday at 10 a.m. Pacific. You're welcome to join that on our YouTube page and ask any questions. We'll have experts who can answer them. So we're going to launch next year, October of 2024. And we're going to have a Mars gravity assist soon after that in February of 25, back around to the Earth for an Earth gravity assist in 26, and then out to Jupiter orbit insertion in 2030. And that is just going to be amazing. So here's what that orbit insertion might look like. So basically here you're seeing the magnetometer boom, which has now been deployed. Here's the spacecraft as we fly in. We, turn our spacecraft around and we basically fire all of our engines for, I think it's about an hour and a half or something, just to slow down enough that we can be captured into orbit around Jupiter. So this is really one of those critical maneuvers that has to take place. Otherwise, we're just going to keep going and we're never going to get to see Europa. But once we make it into that orbit, around Jupiter, we'll start to sort of like circularize. We'll start out in a very long elliptical orbit. We'll work our way down so that eventually we'll be taking these 50 or so close flybys by Europa. But it's going to be amazing. It's going to be an amazing mission. It's going to capture images with all of those different instruments, and we're going to see Europa in a way we've never seen it before. And one of the really exciting things we're also going to be able to do is we're going to be able to bring the general public along with us, including you, everyone listening on this call. So you can send your name to Europa with our Message in a Bottle campaign. So we're basically inviting the public to join the mission and to add their names to a poem written by the US Poet Laureate, Ada Limon. And so the names of the participants who sign on to this message, the message being the poem, as well as the poem itself, will be engraved on the Europa Clipper spacecraft, and they'll travel to the Jupiter system. So if you go to the website here, the Message in a Bottle page, you can submit your name. The campaign will run until December of this year. So, get your names in sooner rather than later so that you can join us on board, and you'll get a custom piece of artwork as well. And so here's just a few shots from the launch of this campaign. So here's Ada Limon, the US Poet Laureate. She's really just an amazing and fantastic human being who also turned out to be a space nerd. And so she was a perfect match for this project. So here she is at JPL, looking through the window of the clean room at the Europa Clipper spacecraft being assembled, as well as meeting Lori Leshin, who's the JPL lab director, and getting to do a little tour of JPL. And then we had a kickoff campaign at the Library of Congress on June 1st, where we launched this whole Message in a Bottle campaign. We had an exhibit that was open to the general public, as well as a panel discussion. I think you can find the recording of this panel on the Library of Congress YouTube page, and it's really fantastic. It's well worth watching. We had some exhibit of artifacts from the Library of Congress's extensive collections, including an original copy of Galileo's book, The Starry Messenger from 1610. So it's pretty amazing to see that just sitting right out on a table in front of you. And here's the message. So this poem is read by Ada Limon, and this is the message which will be engraved on the spacecraft. So let's just take a minute and listen to it.
In Praise of Mystery, a poem for Europa. Arching under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky. The whale song, the songbird singing its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water. Each drop of rain, each rivulet, each pulse, each vein. Oh, second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark.
Gets me every time. Okay, so that poem, as well as the chips with the names of those who sign on to our campaign, our Message in a Bottle campaign, will be engraved on this panel here, which is a plate that'll go on the outside of the vault, the radiation shielded vault, and the poem and the chips will be kind of on the inside of this panel to protect them a little bit. And so that's why those names need to be collected by the end of December, so that we have time to get them on the chip and they don't miss their ride to Europa. So please do consider submitting your names. Here's what one of the chips will look like. We're hoping to get 1 million names, 1 million people signing on to this. And I think we're already at about 350,000 or something like that last time I looked. So we need everyone we can get. We want to beat Mars. Little friendly rivalry here. So here's what the campaign looks like, where you can sign your name. There's also a version in Spanish. You can see where people have participated. And then once you do that, you get a custom certificate, which is with your name on it. And so we have a bunch of other pretty cool resources on the Europa Clipper website. I already mentioned the Clipper Cam, where you can watch the live feed as the spacecraft is built. There's an AR experience that you can get where you can have Europa in your own living room. We have activities for kids, such as coloring sheets, educational activities. There's posters, there's stickers. There's a model for a toy brick, so a Lego style model. You can download the instructions to build your own. And there's even a poetry lesson, so you can write your own space poetry. So there's really something for everyone. You can get to those resources by scanning this QR code or by going to europa.nasa.gov/participate. And so we're adding more materials all the time, and we really just want to bring everyone along for the ride with us. So I work with I'm the project science communications lead, and so I work with an amazing staff in our public engagement and media and social media departments at JPL. And we also invite you to follow us on social media. We have a great website at europa.nasa.gov. We're active on Twitter and Facebook, as well as Instagram. And so with that, I'll pause for now, and I'm very happy to take any questions that folks have. Thank you.
Oh, wow. I'm sure I'm not the only one in tears right now. That was such a beautiful poem and such a lovely presentation. Thank you so much for sharing with us.
Thank you.
It's Reet. Oh, yeah, there you are. Excellent. Oh, we have so many questions. I hope we can get to some of these before the top of the hour. A lot of people wanted to know if Europa is the only moon that's going to be seen, or if there are any others that the Clipper mission will take a peek at while it's, making the rounds.
Yeah, so that's a good question. And it's a bit of a a complicated answer. So the European Space Agency has already launched a spacecraft called JUICE, which stands for the Jupiter Icy Moons Explorer. And so JUICE is already on its way to the Jupiter system. It's going to focus on Ganymede, but it will also take images of Io and Europa and Callisto as well before it actually goes into orbit around Ganymede. Ganymede doesn't have nearly as bad a radiation problem as Europa, and so you can orbit Ganymede much more easily. Europa Clipper will get there about a year before JUICE does. And so the two spacecraft will actually be operating at the same time in the Jupiter system. And so yeah, we are hoping that we can use, there are a few flybys that we have of Ganymede and Callisto kind of on our way into Europa. So yeah, we're hoping that we can take some observations. It'll be really interesting, not just in their own right, but also to kind of compare the observations that JUICE is going to be taking. So yeah, so we're still working on those plans. Officially, we're only allowed to look at Europa, but unofficially, we might take some calibration images of some of these other worlds. So stay tuned.
Oh, that's so exciting. I love when we work together all over the world. There's a question from Stuart about where did all this water come from?
That's a really good question. So we think it's been there since Europa formed. So when you look at the solar system and when you look at kind of how we think the solar system formed, sometimes people like to think of what's called the snow line, which is sort of like an imaginary distance between the orbit of Mars and Jupiter. So clearly when the solar system was forming, something happened where the inner solar system has, Mercury, Venus, Earth, and Mars. Those are all relatively small, rocky planets. They have some water on the surface, but, not a ton. And then you get out to the outer solar system with Jupiter, and suddenly you have this gigantic gas ball. And so we think that one of the reasons why Jupiter is where it is that was the distance from the sun when the solar system was first forming, where it was finally cool enough for some of the gases that formed Jupiter. So, hydrogen, helium, stuff like that, to kind of condense and start to form these gas giants. So some of the material that was left over from that formation is what formed the Galilean satellites. And so we think that there was a lot of, kind of what we call volatiles, which is, hydrogen and oxygen are both very common in the solar system, kind of the universe. And so water is a very common molecule. And so we think that this water was there when it formed. We think that even Io probably had water when it formed as well. It's just that all that volcanic activity has really driven off a lot of the water. There's another theory that says that the water was delivered later on. Maybe it was delivered through a whole bunch of comet impacts. So that is kind of, up for debate in the science community. But the more generally accepted view is that, yeah, that water was there when it formed. Worlds like Callisto have, a much higher kind of like mass percentage of water ice than even a world like Europa. The ice layer goes down much closer to the core in a world like that.
Wow. So one of the questions we also got that I think you just answered is, these are not captured satellites, for example, like Mars's moons. These were made in the process of Jupiter forming. Is that
right? Right. And that's one of the really cool things about studying the Galilean satellites is that, in some ways it's like a mini solar system. Until we started finding exoplanets, like, I guess I'm old. I'm not that old, but I'm old enough, right? So like when I was in college, there weren't any exoplanets. Like we hadn't found any yet. There was still, it was kind of like crazy talk. Like the exoplanet people are like, oh yeah, you're never going to find this. And so, we had kind of our own solar system was really the only model of solar system formation that we had. And so people would often use the Jupiter system to kind of help test their models of solar system formation, because you had kind of a protoplanetary nebula basically around the sun that kind of formed the planets out of the leftover sun material. Then you have kind of like another cloud of material around Jupiter as Jupiter was forming, and clumps of that stuck together and formed this nice regular satellite system as well. So yeah, we're pretty sure that at least the Galilean satellites formed in place. It's possible that some of the smaller, weirder satellites of Jupiter that are further out could have been captured.
Really cool. We have had a lot of questions coming through. And if you have any questions for the speaker, go ahead and throw those in the Q&A window. We'll try and get to as many as we can. And so, John asked a really interesting question. In 4 billion years, why has this ice not sublimated? Why has it not just disappeared?
Yeah, that's a good point. So some ice is lost off the surface, but not that much. Because it's really, really cold. And so what that means is that, there's a vacuum. So there's no atmosphere above Europa. And so yes, some materials lost through sublimation, but basically it's so cold, the ice is so hard that it's really pretty stable on the surface. You do have a very slow kind of mass loss rate. Some of the material might be lost, say, through sublimation, or, you can knock off material through impact gardening, through sputtering as well, through charged particle and micrometeorite impacts on the surface. Some of that material does end up kind of going into orbit, say even around Jupiter, and then just reaccreting on Europa. So it kind of, goes around and then it gets stuck back onto Europa again. And it's big enough that it's relatively hard to kind of lose material from it as well.
Wow. That's pretty incredible that it catches up with its own water on the way back around. We'll put a lot of these links in the chat. There's lots of questions like, I want that poem, and where do we find this and that? We'll make sure to put those in the chat. Thank you all. There's a question, Dr. Phillips, about how you got started. What brought you to this mission and to space exploration and planetary geology?
That's a good question. So I grew up in, near Boston. And so my dad was a really avid amateur astronomer. And so he would always, haul out the telescope, and somehow it would always be, late at night, and it'd be freezing cold in the middle of winter. And he'd spend an hour trying to get, some galaxy or nebula in the telescope. And, I'd look in it and I tried to be appreciative, but I was a kid and it was cold and dark and late. And I was just like, it was always disappointing, right? Because it never looked like the pictures did. And so I decided I wanted to major in physics. I liked science. And when I was in high school, the Voyager spacecraft flew past Neptune. And they're on, this is, like pre-internet. And so the whole science team had to go to JPL, to the, mission control room, to watch the images coming down. And they had a live stream, but, the 1980s or version of a live stream on PBS on TV called Neptune All Night that was broadcast basically from there. And they just had a camera feed from the control room where all the, like Carl Sagan and all these scientists were there watching these pictures come down. And so I persuaded my parents to, let me stay up all night to watch this thing on PBS. And oh my God, it was amazing, because this was the first time that humans were setting eyes on the moons of Neptune, and they were amazing. And so I remember, this moment of, this picture comes and it's, crazy looking moon, and no one had ever seen anything like this before. And I remember Carl Sagan saying, wow, I have no idea what that is. And that was just a moment for me where I was like, there are things that we haven't found yet. There are things that humans are seeing for the first time. And I was hooked. I was like, I want to do that. I want to be the one in the control room seeing the pictures when they're coming in. And so, I went to college, I majored in astronomy because, as one does, right? And then, after classes on galaxies and stars and nebulas, I was like, okay, when do we do the solar system? And they're like, oh, that's actually planetary science. That's, so I was like totally in the wrong major, but, eventually I found my way to planetary science, and I, went to grad school. My timing was perfect because the Galileo mission was about to get to Jupiter the fall that I would be going to grad school. And so I basically, again, pre-internet, I did a whole bunch of sleuthing to figure out where members of the Galileo imaging team were, and I applied to those schools for grad school, and I was fortunate enough to get into the University of Arizona to work with someone on the imaging team. And sure enough, as a grad student, I got to be there. I got to be the one who was, like the youngest one who could use the computer best, who could pull down the images and pop them up on the screen and have all the professors crowd around me and say, wow, I have no idea what that is. And it was amazing. So ever since then, I've been waiting for the next pictures of Europa. And it's, another 6 years. I can do it.
I have no idea. Sometimes the most exciting.
It's the best.
I love that. I love that you came by it naturally too. This is what we do all the time as amateur astronomers. We're glad
Absolutely.
it has effects as we go along. I'm really excited that, and I hear that my kid does not want to come out in the cold with me either.
But do it anyway.
Yeah, but we do it anyway. You never know where it lands. Oh, all right. We've got a question from Chris wondering if detection of life is potentially possible through a combination of the data from the payload instruments. I mean, is there any chance we might?
Yeah.
detect?
I mean, certainly there's a chance, right? We're not expecting the spacecraft to get whacked into by a fish that gets thrown off the surface, but if there is one, we'll certainly take it, right? I mean, we're not expecting there to be fish on Europa, but it's possible that there could be microscopic organisms that we could detect. If there are plumes erupting from Europa, we think there could be. There's kind of some sort of evidence that's inconclusive, I would say. But if there is a plume, the spacecraft will be able to fly through it and actually sample it with that mass spectrometer, so that the dust and the gas detector, basically. So yeah, it is certainly possible that we could find, evidence maybe of life. It's not, I wouldn't say it's likely, but it's within the realm of possibility. That's one of the really exciting things about this mission.
I think there's going to be a lot of, what was that? We don't know.
Yep. And that's the good stuff.
That's great. Wondering what happens at the end of the mission. Ken's asking, is it going to impact somewhere?
Yep. That's a good question. So Europa, one of the things we have to be very careful of is called planetary protection, which is basically, we don't want to destroy life on Europa in the act of detecting it. And so we want to be really careful not to crash into Europa. They're building the spacecraft in the clean room. And so you saw in those pictures, people are wearing like the full-on bunny suits. So it's a very high level of protection that we have to do to sterilize the spacecraft. But even with that, we want to make sure we don't crash into Europa. So the plan is actually to crash into Ganymede. And that's because, while Ganymede does have an ocean, the ocean is much deeper below the surface. So the surface ice layer is, hundreds of kilometers thick. And so, while maybe there's a chance of life on Ganymede, it's much lower possibility. And even if there is, if we crash into the surface, the chances of the spacecraft kind of working its way down into that, very deeply buried ocean on Ganymede were much lower. So basically, the NASA Planetary Protection Office judged Ganymede as a suitable impact site for us. So that's our current plan, is that at the end of the mission, we're going to save enough fuel for kind of a final hurrah to crash into Ganymede.
Wow, I was not expecting that. That's
yeah.
I would have guessed Jupiter. It's like a big vacuum cleaner that cleans up the rest of the solar
Right,
system.
but it actually turns out that it's harder to get to Jupiter. So we'd have to save a lot more fuel if we wanted, it's called disposal. So if we want to dispose on Jupiter, we have to save a lot more fuel. So we can't do nearly as many flybys. If we dispose on Ganymede, it's easier to get there. And so we can have a better chance of, if we're so lucky, getting an extended mission and, get as much science as we can before we have to go down.
Wow. Really cool. And what years are we expecting this to reach Europa?
So it'll launch in 2024, so next fall. It'll enter the Jupiter system in 2030, so a 6-year cruise. And then it's going to be about a year and a half of sort of like getting the orbit ready to start these close flybys. So we might get a few pictures when we first get there, but it's going to take, we're going to have to be patient, right? We're going to have some of those, quote, calibration flybys of some of the other moons. Maybe we'll have a distant flyby of Europa before we get into these much closer ones.
Wow, it's hard to wait that long, but I'm really excited to see. There's a question from Bill too, who once heard a presentation about Europa where a vehicle might have a heating system to melt its way down past the ice. Is that still a possibility?
Yeah, so everyone wants to get into the ocean. So first, we need to study it from orbit, and so that's what the Europa Clipper's mission will do. And so then the next mission will probably be a lander. So for anyone who saw 2001 or A Space Odyssey, or in 2010, there's this great phrase, all these worlds are yours except Europa. Attempt no landings there. We actually did get permission from Arthur C. Clarke to land on Europa. True story. I was there. So we don't have to worry about it. We can actually land. And so one of the probably the next step after something like Europa Clipper would be a lander. And so I actually worked on a project where we were designing a mission to land in Europa that unfortunately wasn't able to move forward. But we're hopeful that, at some point in the future, maybe once we get all these amazing Europa pictures, everyone was like, oh yeah, of course, we got to land. So you land, and then, you study kind of the surface composition, you figure out like what the surface is made of and kind of what its physical and chemical structures are. And then maybe the next mission would be something called a cryobot. And so, yeah, that's one of these kind of melt probes where, you take advantage of the fact that the surface is ice, not rock. And so you could bring, a small sort of nuclear powered heat source, and basically you can just melt your way down. And, over the course of like a year or two, you could actually get through that ice layer into the ocean. And we have, people working on designing these cryobots and testing. They're going to be testing them, in the Arctic and Antarctic. So it's a complicated problem, but it's conceivably doable. And so, yeah, trying to get all the way through that ice layer into the ocean would really just be amazing, right? That's really where, if you're going to look for life on Europa, you want to get into that ocean. So, stay tuned. That's probably going to be, my grandchildren are going to be doing that mission, but I can't wait.
Yeah, we all want to know. I mean, is it possible there could be life on the surface of
Yeah, so probably, any light, so the surface of Europa, it's exposed to just blistering radiation. It's about 100 Kelvin, so it's really, really cold. There's no atmosphere, and the radiation environment would, be really toxic to any kind of life forms that we know. So we think it's really unlikely that any life could be up at the surface. It's possible that, maybe there could be kind of like remnants of life. So sort of biosignatures, so biomarkers, materials that could have been formed by life that we can detect and say, yeah, that looks like it was created by life, either at the surface or more likely, when you get down about 10 to 30 centimeters below the surface, you're shielded by the ice from a lot of that radiation. And so we think that biosignatures could survive once you get to a fairly shallow depth. And so that's what maybe a lander could do, is kind of dig its way down a little bit, scoop up some material, bring it on board and study it. But really, when we're talking about life, it would be much more likely, maybe in some of these kind of subsurface liquid pockets within the ice, but much more likely in the ocean itself.
Yeah. Wow. And hopefully in those plumes, we might be able to detect something.
Right. Yep, for sure.
Out at us. That's exciting. Okay, so now people are going to be, the last few questions that we've gotten, we're getting concerned about how it's doing and how it's getting there. Is there any worry about going through the asteroid belt without damage? And then once they get there, what about those rings? Any chance they could cause damage to the solar panels?
Yeah, fortunately, the asteroid belt doesn't look anything like Star Wars, where it's all these rocks that you have to, like kind of go in and out and bound, right? It's pretty straight out. And we have very good models of exactly where kind of the big objects in the asteroid belt are. And so, yes, while we will have to fly through there, many spacecraft have done that before. And so our navigators know exactly how to design a trajectory that will take us far away from anything dangerous. Small meteorite impacts they're always a hazard. The solar arrays will probably get hit by kind of micrometeorites. But, again, it's kind of a known hazard. We've, had many spacecraft that have made it to the outer solar system safely. And so, it's a risk, but it's judged to be a relatively small risk. And Jupiter does have a ring system, but again, it's a very sparse ring system. So it's nothing like Saturn's ring system. And we know where the rings are. And so we can, kind of stay well away from any places where there's a higher density of potentially hazardous objects.
Wow. Well, Dr. Phillips, I just want to thank you so very much for sharing all of this great knowledge and with such an engaging presentation with us tonight.
Oh, you're welcome. And thank you for some really fantastic questions. Thanks to our audience. This was really fun.
There were so many more questions than we could get to, but thank you all for sharing with us. I'm going to stick in the chat. There's just a quick survey about what you'd like to see next, what you learned, and why you might want to see in future webinars. And I just want to let everybody know you can find this webinar along with many others on the Night Sky Network YouTube page. And we have some cool upcoming ones as well. The Euclid mission will be in August. We're still waiting on a final date for that. We also have August 23rd, an International Observe the Moon Night webinar with Andrea Jones and friends. On September 19th, we are going to learn about the lunar South Pole with Dr. Erwan Mazarico. And we'll have one more enrichment webinar about the eclipse coming up. So, gosh, I just thank you again, Dr. Phillips. What a treat to have you here. Thank you all so much for joining us, and we'll see you in about a month. Keep looking up, and good night. Thanks, you all, and I'm so sorry about the chat. We'll get that figured out for next time. I appreciate all of you sticking with us. It was, I think, one of the best attended